We now want to conclude the second chapter on our analysis on the locally compact abelian groups by this big theorem called the Pontryagin duality. So essentially, this theorem states a very nice result, just saying if you take a locally compact abelian group, let's say G, this locally compact abelian, then automatically you know the dual group is also locally compact abelian, so you can consider its dual group. So you do the double dual group. The idea is that this one is in fact just the G itself. Okay, so that's called the Pontryagin duality. And the idea is fairly simple. So you kind of see this construction when you consider, say, the double dual space of some Banach space or a Hilbert space. So if you have any, say, X inside G, so there's one way of embedding an object into the double dual space by defining this kind of evaluation map. So you define X hat from the G hat to the complex, or basically to the unit circle, by doing the following. If you take any character, you just evaluate at this point X, okay? So this is essentially the same idea as the double embedding some Banach space into its double dual, okay? So one thing now here, well, we're not at a linear space, so we're at a group. So this X hat is clearly going to be a homomorphism. X hat is clearly mapping this G hat to this T is clearly a homomorphism because the multiplication on your dual group is just pointwise multiplication. So your X hat is a homomorphism, and it's also going to be continuous. The reason it's continuous is the following, because we prove the fact that if you consider this joint map, you take an X from G and you take a phi from G hat, and you just map it to the phi of X, which is inside the T or the complex, well, then this map is going to be continuous. So because you have this kind of continuity, so once you fix a particular X and you just treat it as a function that maps from G hat to the unit circle, then you still have something that's continuous, okay? So that just shows that this X hat is also inside the double dual group of G, so just as we expect it to be. All right, so and moreover, I want to point out one thing. So if you recall, we know this G hat, they will separate points on this G, okay? So on G. So in other words, if you have any X and Y not the same on G, then you can find some character that identify these two, okay? So this only happens when we have a abelian groups here. So you can see they're different by some character, okay? So phi X is not equal to phi Y. And because of that, you can say, well, this X hat now you now can see the difference between X hat and Y hat, okay? So they are also not the same. So in other words, this map from G to G hat, so let's give it a name, let's maybe call it big phi, that's going to be injective, okay? So as long as you have two different X, then they will see they're going to be different under this embedding. Okay, so I should say double hat here. Okay, all right. So the idea is that the theorem of Pontryagin duality is just showing this phi not only is injective, is actually a bijection. Okay, so you have two topological group. It's not only a bijection but also a isomorphism as topological group. Okay, so the theorem Pontryagin duality says G and G double hat are isomorphic via this map phi, okay? So this theorem, the proof is kind of difficult, so let's divide it into three parts. So let's say there are three steps. In the first step, which I'm going to show in this video, is that I want to show that phi is a homeomorphism. Of course, is from G to its image, so G to phi of G. So here, phi of G, we know phi is injective, so phi of G is some subgroup inside the double hat of G. And we just want to show that this phi is going to be a homeomorphism between, I know it's injective, I just need to show it's continuous, and the inverse is also continuous. And second, I want to show that this phi of G, so this image, so I want to show this is essentially the same as the double dual group. So first of all, I want to show it's going to be a closed subgroup. And finally, I will show that it's not only closed, it's also dense inside the double dual group, inside G double hat, okay? So that's kind of the outline of this proof. So in this video, let's just prove the first one. So to prove the first one, essentially I need to show that this phi is continuous. Okay, I know it's ejective, so it's a bijection between G and its image. Okay, I need to show it's a continuous, and the inverse is also continuous. So in other words, I need to show it maps some open bases to some open bases. Okay, because we're at the topological group, we just need to consider the basis at the identity. And let's just recall a fact back then when we talk about the topology on G and G hat. We did something like that. So if you have, say, you have a K inside your G, and let's say for every epsilon greater than or equal to 0, and you can define some map, let's say nk of epsilon, which is equals to all the phi inside G hat, so that this phi, when you evaluate at points in K, that's going to be close enough to 1, or you can think about this 1 as the constant, well, the unit character evaluated at x. Okay, so that's less than epsilon. That's for all x inside K. And they actually form a neighborhood base at the identity, the phi of identity. Okay, so they are both open and form a base at this phi of E. Okay, so that's what we proved. So immediately you have a pretty good description of the neighborhood base at the double dual group. Okay, so as a result, we have that for every K inside, I should say this K is compact. So if you just do the dual version of this, so for every K inside the dual group compact, and for every epsilon greater than 0, and you define something really similar, you do nk of epsilon, you consider all the phi inside the dual of the dual group, which is just the double dual. So let's just use phi hat to denote something in the double dual group. And so this phi hat evaluate at any, your group now is the G hat. So if you evaluate at, say, psi -1, that's going to be less than epsilon. That's for all psi inside this K. Okay, so this K is a compact subset of the dual group. We know these kind of nk epsilon are going to be a neighborhood base at the identity of the double dual. Okay, so they form a base at the identity inside the double hat. And by the way, this identity in the double hat it has to be the evaluation map at the identity. Okay, because it's the dual group of the dual group, so it has to evaluate each of these dual group element to 1. So that's essentially the same as evaluating at the identity. So let's just use E hat as the identity element in the double dual group. All right, so we now have a pretty good idea what's the topology base at the identity at the double dual group. But we now need something quite similar for the identity base at the original group. So if you recall, we actually, when we proved this fact that these nk epsilon form a base, we actually also defined something similar for open sets inside G. So if you consider all the mk epsilon to be all the x inside G, so that if you evaluate, let's say, let's use the same notation psi, evaluate x -1 less than epsilon for every psi inside K, we know they're going to be open. Okay, so we didn't really show they are a topology base, but we know they're open, basically follow a very similar proof. And the first technical lemma we need to show is that these m of k epsilon are actually a neighborhood base as well. Okay, so it's a base of topology on the G, well, of course, at the identity. Okay, so at identity. All right, so how to show this? Well, let's prove this fact. So for every identity open neighborhood around this identity, let's say V, we can, because we have some locally compactness, we can just always pick some compact set W, let's say W compact, and we can make sure this W is kind of contained inside V, so it's some small neighborhood. So let's say W and W inverse is contained in V. And we can, of course, make the W also a neighborhood of the identity. And we can also make it a symmetric neighborhood. Those are kind of the easy stuff, all right? So once we know that, well, let's define some function. So if I let f to be this function of the characteristic function at w, well, I want to normalize it by the Hart measure of this w to the half. Okay, so mu is the left Hart measure, or just the Hart measure. And we do this kind of the standard trick we have seen several times right now. So you convolute f with its own involution. Then we know this one is, first of all, is in L1, okay, because f, I normalized the f so that, well, here W is compact, so f is certainly in L1, and then normalize it. And so when you do the convolution, it's still in L1. And moreover, because you're convoluting something with its own involution, you have something in a positive definite function, okay, so G is positive definite. And moreover, if you think about when you convolute two things, the support is going to be contained inside the support of f multiplied by the support of its involution, which is w times w inverse. And this one is going to be contained in V, okay? So that's from our choice of this w. And moreover, if I consider its Fourier transform, then I have that we saw that several times as well. So its Fourier transform is essentially just the Fourier transform of f, norm squares, and it's going to be positive, okay? So by the Fourier inversion theorem, so let's just say Fi, okay, so Fourier inversion, if I compute the G of B, and when we did the Plancherel, actually we saw that this calculation, you can convince yourself this is just the fx squared dx, okay, that's going to be equals to 1. All right, this is just by our choice of f, I normalize it by the mu of this w, half of that, and now you take the square, so everything integrates to 1. But on the other hand, that's also the 2 norm of the f hat, or another way of saying this is essentially integrate this g hat of phi, and you do d phi, okay? So you integrate on the dual group. All right, so now because you have this integral of this g hat is equals to 1, and you know this g hat is greater than or equal to 0, so you can find some compact set where this integral is kind of concentrated on this k. So you can always find some k which is compact, so that if you do the integral on this k of this g hat, d phi, that's going to be greater than, let's say, 2 over 3, okay? So in other words, if you do the integral on its complement, that's going to be less than 1 over 3, okay? So your integral is kind of concentrated on this k. And if you consider for every x inside this M of, let's say, something concentrated on k and 1 over 3, well, let's think about what happens to the gx. So the gx, the value of gx, that's just going to be equals to the integral of, by the Fourier inversion, you do the g hat of phi, and then evaluate phi x d phi. All right, and you realize, well, this is going to be equals to, you break this integral as integral on k and integral on the k complement. Okay, so let me just copy it down here. All right, on the k, so you see that this phi of x, well, is the real value of this, because x is going to be close enough to 1, okay? The phi x is going to be close enough to 1. That's essentially what the set M tells you, okay? So let me just remind you, phi x minus 1 is going to be greater than, less than 1/3. So we know that the real part of this is going to be greater than 2/3, okay? It's close enough to 1. And so you integrate this whole thing, and so this one is going to be greater than something like 2 or 3 times the integral on k of the g hat, and the integral is greater than 2/3, so you multiply 2/3 again, so that's something greater than 4 over 9, okay? Something bounded away by 0. And the second part is that, well, you add another thing, so if you do the absolute value of this, that's going to be less than equals to the absolute value of the integral g hat d phi, while g hat is positive, but you're integrating on the complement, and this one is going to be less than 1/3. So when you have something greater than 4 over 9 and you plus something with norm less than 1/3, this whole thing is going to be greater than 4 over 9 minus 1/3, which is still bounded away from 0. Okay, so this is still greater than 0. So in other words, your x is going to be inside the support of G. Okay, so the x is inside the support of G. So this just shows that the set M of K 1/3 that's going to be contained in the support of G, but your support is actually contained in V. So now you find some of these MK epsilon inside your open neighborhood V. So you have that these M also form a base of topology. So as a quick corollary, now we can just show this phi is we defined from G to G double hat is a homomorphism. Okay. So if you take any K which is compact inside G hat, okay, and so you can think about this. We define this NK epsilon to be all the phi hat inside G double hat, so that the phi hat evaluate at any psi inside this compact set is less than epsilon. So for every psi inside K, and this is a base of topology at the identity at the double dual group. And you define this other thing, M of K epsilon, to be all the x inside G, so that this phi x minus 1 is less than epsilon for every, you shouldn't say phi, I should say psi here. So psi inside K, okay? So this is another topology base at the identity on your original group. Well, one thing to look at the second set is that you can treat this x as in the double dual. Basically, that's the x hat. So this is the x hat evaluate at psi minus 1 less than epsilon, okay, for every psi inside K. And as you can see, if your x is inside the second one, it has to be inside N as well. So this is essentially just the N of K epsilon intersect your the image of this phi you're embedding, okay? So based on that, well, you have basically this phi when you map from x to the x hat, you have something that transform your topology base, okay? So because N, M, they're both their topology base. So in other words, if you have some x alpha converge to x inside G, that's just going to be even only if the phi of x alpha converge to phi of x inside the G double hat, okay, because these topology base are kind of connected. So from there, we know this phi is a homeomorphism, okay, so phi is a homeomorphism from G to phi of G. So here the phi G, we basically equip the relative topology here, okay, so this is the relative topology on phi G. So this finished the first part of this theorem.